Okay, so today's plan is first I would go through one problem from last homework, and then I would go through another one effective Hamiltonian theory, which is equivalent to the perturbation theory in learning class. Okay, so the problem I would like to go through is the okay, chapter 4, problem 5. Yeah, by the way, in the future, if you have any specific problems you want me to go through in the discussion, just let me know. I can do it. Okay, so this problem, yeah. Okay, so imagine you have an atom and there's an electron. Um, Electron spin 1/2. Of course, we usually start with a Hamiltonian looks like this. We have some kinetic part and also some potential. And we also have some spin orbital coupling. Then this guy would give us the eigenstate like N, L, J, M, right? L stands for the orbital quantum number. This J is the total, like a J equal to S plus L, meaning that this J must equal to L plus or minus 1/2, right? This M stands for the JZ, the a component of this total angular momentum. And now, okay, so the problem tells us there's a small perturbation, lambda delta R, something like this. By the way, feel free to stop me if you have any questions or get confused. And in this case, from the perturbation theory, we know the eigenstate would shift, right, to some superposition of other states, N prime, L prime, J prime, M prime, and there's some coefficient and superposition of this. And this coefficient is given by the standard perturbation theory, N, L, so N prime, L prime, J prime, M prime. V is the uh, um, perturbed energy potential, and L and J, and the denominator is the difference of the energy. So now the question asks you, first, from the pure symmetry point of view, what constraint we have to make sure this coefficient is non-zero? So first we look at the symmetry. Basically, we want to start from the symmetry of this potential. First, okay, so this potential, since you notice that this guy is made up of this kind of S dot P, this is a scalar, right? Meaning that if you rotate, this guy remains invariant. And according to the Wigner-Elkhart theorem, this implies your J prime must equal to J and M prime must equal to M, right? Because, okay, let me write this. Because this V is a scalar, then this guy is proportional to J prime, M prime, Jm. This guy would tell us this constraint, right?
Can you explain it more?
Sorry?
Can you explain it again?
Okay, so V is a scalar, right? Like it's like a rank 0 spherical tensor. Right? And remember, like according to the Eckert, Wegener-Eckert theorem, this guy equal to some J prime, M prime, and zero. In this case, it's 0, 0. So it's like I have a spin J object plus a spin 0 object. It's still spin J object, right? So it's yeah, it's nothing fancy. It's just like this. From
so is it because like a scalar is a
scalar is just a scalar, right? It's like a spin 0 object, yeah. Because it remains unchanged under rotation. If it's spin 1 or spin some finite number, then it will rotate under some rotation. If you rotate the system. So this is nothing but the Wegener-Eckert theorem. So this would implies this constraint. There's another symmetry associated with this V is so under parity operation, this V will flip the sign, right? Because the spin remains the spin, like S is S, but P would become minus P. So V would flip the sign. So this means this state and this state must have different parity. Otherwise, it will be 0, right? So to make sure they have different parity, this L, the difference between L and L prime must be an odd number, right? So it's like a L prime must equal to L plus some odd number.
Could you explain why that is?
It's because like this kind of state, if L is odd, then this guy would become minus this guy under the parity operation. If this guy is even, then under parity, it remains the same.
And is this due to the radial part of the wave function?
No, it's the angular part. It's the L. It's due to the L.
Okay, I guess I don't see. I mean, is this something we should just know, or can we show why?
I'm pretty sure it's in the textbook. Like basically, if you have a parity operation acting on this state, you get something like this, something like that, or it's just LM, something like this.
Is there any clearer ways to get it without looking at the YLM? Like looking at the
right, it's like okay, because okay, I guess we know that so for like infinite no, deep well, like n equal to 0 is something like this, n equal to, oh, sorry, n equal to 1 looks like this, n equal to 2 looks like this, n equal to 3, I don't know. So basically you can say the wave function, the parity of the wave function kind of a switch when you go from even number to odd number, from odd number to even number. You can see the pattern here, right? Similarly, in the orbital case, also the same. And if you look at the expression of this guy, I'm pretty sure. I'm pretty sure you can also say something just directly from the wave function. So you didn't go through this in the class?
I don't think so.
I think we're elaborate, like he elaborated on this point.
I see. So basically it's like this this kind of a phenomenon happens in many situations, right? Whenever you kind of switch like from odd eigen state to even eigen state, the parity change. Like the harmonic oscillator also similar, right? If you kind of draw the wave function, I'm pretty sure.
Yeah, but that doesn't sound like so safe to me, because for this problem, for example, you like the pair didn't change with M but only with L. So is there any way to get this -1 to the L without looking at the explicit expression of the wave function, but like through the manipulation with the eigencats and some operators?
I don't think so, because it's like eventually, this kind of a operation, let's see. So remember, this is a parity operation. This is equivalent to send your theta to a theta should be pi minus theta, and phi to phi plus pi. And you will say your wave function with finite sign if your L is odd and remains the same if L is even.
All right, I'll probably just remember that.
Yeah, I mean, it's I guess it's a property of this kind of spherical harmonics, and I'm not sure what's exactly question you're asking. Yeah, but
can I ask a slightly different question? I guess probably more geared toward the perturbation theory aspect of it.
sure.
So I understand that this V is going to take odd parity states into even parity states and
Right,
vice versa.
right.
How do we know though that, like, apparently we're supposed to make the leap to like only parity states that are different from the initial state are supposed to be in the perturbation expansion? Like, how do we know there wouldn't be like even and odd parity states that are in the perturbation that just flip to each other under V? Does that make sense?
Wait. So this is a first order perturbation, right?
Yeah.
It's like so the coefficients is given by this expression, and so what do you mean by like so can you ask your question again, like the?
Yeah, okay, I think that kind of answers it. But the question was just like, how do we know from just the fact that V maps even to odd states and vice versa that there are only going to be states with the opposite parity in the expansion? But I think the answer is just like, that's to first order, correct?
Yeah, of course. If you go to a higher order, I guess it's more complicated, right? but you can still look at the coefficient, the expression of the coefficient, and look at the parity, and that would impose some constraints, I guess. So first order is very clear. It's like this guy, if this guy is odd, then include the V is become even. And so this state must be also even. So the cat and brown must be different under the parity operation. Yeah, so basically this is a constraint we have due to this parity operation. But at the same time, we know that, where's the expression? Okay, so at the same time, we know this J is L L plus or minus 1/2. And this J is also, J prime is L prime plus or minus 1/2. And remember there's another constraint is J prime equal to J. This tells us your L prime must equal to L plus or minus 1. Because if your L equal to L plus 2 for 3, for example, then this constraint cannot be satisfied. So eventually from the symmetry point of view, we get 3 constraints. One is J equal to J prime, M prime equal to M, and also L equal M, L prime equal to L plus or minus 1. So another I guess the second question I ask you to do is write down the expression and say what else, what other constraints we can have, right? So nothing fancy, just write it down. You know, it's kind of standard. I assume the angular part is the wave function is psi, then it's L prime, J prime, M prime, V. So V is given by delta R and S dot. So in the real space representation, the P is, the momentum looks like this. And O. Something like this. So you can say because there's a delta function, to make sure this guy is non-zero, we require this guy is non-zero or this guy is non-zero, right? On the other hand, we know this guy looks like this. The rate of wave function looks like this. So this implies your L is 0. This guy implies L prime equal to 0. This guy implies L equal to 0. If your L prime equal to 0, then your L must be 1. This guy implies L prime must be 1. So this are only 2 possibilities.
他在讲作业，挺好。
Any question?
Can you just go over that last line? So I understand the delta functions are going to be isolating the radial wave function.
Right.
Can you just go over the last line of logic one more time?
Okay, sure. So, okay, basically, you understand this guy must be non-zero or this guy must be non-zero, right? To make sure you get non-zero results. And this guy non-zero implies your L prime must be non-zero because your looks like this. So you want your this power to be zero, right? So L prime to be zero or L to be zero. If your L prime is zero, remember the difference between those two must be one. So your L must be one. Of course, it cannot be minus one, right? So it must be one. Similarly, your L prime also must be one.
I have a question regarding to parity again.
Sure.
So, the entire function, right, that is this has R component and then spherical harmonics. When you're applying parity operator, you're applying it to all variables, right? So you're switching the sign to all the variables. And some of them are even, some are odd, right?
Mm-hmm.
Or how does that work? For example, if I have R to the R squared, for example, times sine of phi or something like that. R squared is an even function, but sine phi is an odd function.
Same.
So at the end of the day, the entire thing is an odd function.
Right.
So, but that depends not just on L, it also depends, it depends on all of the L's and M's and J's, right? Or no?
It depends on your L and it. Okay, so
Okay, I guess it doesn't depend on J, but it depends on both L and M, right?
So it's independent of M because so it depends on which wave function you're talking about, right? So for this kind of spiral harmonics, it's independent of M because your M. I actually didn't remember exactly. It's like
yeah, it was something like e to the m5, but this is
if your phi goes to if your phi goes to like
so then I have real component goes to is even, but the odd component is imaginary component is odd, right?
Right. It becomes like expansion right. I guess in this case you need to combine with your another piece. Right, it seems not that obvious. Oh, right, because, okay, I just look up on the Sakurai. It's like so this guy is proportional to P, sorry, to the, to this guy. I guess when you change your this guy, I guess okay, so this guy would give us the minus 1m, right? When you shift your phi to phi plus pi, right? And this guy, I would guess there's some similar factor like this, and eventually there's no contribution from the m, and have something like that. But you need to check. I just copy from the book.
Yeah. Okay, because that would make sense.
Yeah, but yeah, you know the how to do it in principle, right? It's like whenever you apply your this priority operation, you just flip out the coordinate and that's it. And see how the wave function change. And maybe when there's some you know, because this kind of a potential, this potential itself or is invariant on the priority, meaning that your wave function must be even or odd, right? It's like yeah. Okay, so that's one problem I want to say about the this kind of oops, homework problem. So the next thing I want to say is about the perturbation theory. So for time-independent perturbation, so there are two types of, you can think of two types. One is the non-degenerate, and another one is degenerate perturbation. So usually what we learned is, okay, given a Hamiltonian, we can separate it into two parts, right? This H0 part is easy to diagonalize, but this part is difficult to deal with. Then we know by applying some formulas, we can calculate the energy corrections to some order you want, right? That's usually what we do. So now I would say there's another approach which is equivalent to this, and I would say it's more commonly used in research. So whenever I remember when I first kind of encountered this formalism when I read some papers. Okay, so they just say, okay, from perturbation, we know the effective Hamiltonian is like this. So I was kind of surprised because I didn't learn this in class. So yeah, I think this might be useful for you guys to know there is such a formula, equivalent formula. So basically the idea here is we know imagine this is the original Hamiltonian or original Hilbert space. But usually the physics we care about only occupies a very small part of your Hamiltonian or a small part of your Hilbert space, right? For example, in this case, if we care about some specific energy levels, then it's just one element of your Hamiltonian, or some degenerate subspace, or only corresponding to some small subspace. It's not whole subspace, right? It's not a whole Hilbert space. So imagine, okay, let's say we care about some small degenerate part. So in real case, the space we generally care about is the ground state. And if the ground state is degenerate, then there may be some, you can form, okay, so the logic here is instead of doing the perturbation directly from your whole Hamiltonian, now from this complete Hamiltonian, we construct some effective Hamiltonian, which only describes the physics you care about. So originally, imagine this, if this is an m by m matrix, and this subspace is like, for example, like a 2 degenerate, the degenerate is 2, then this effective Hamiltonian is only 2 by 2. And by diagonalize, if we diagonalize this effective Hamiltonian, we get some energy, right? This energy is exactly the energy you get from the perturbation from the whole Hamiltonian. Did you get the logic here? So the original logic is starting from the whole Hamiltonian. We do the perturbation, just a formula. You just apply it. So here there's one more step. Basically, from the whole Hamiltonian, we first obtain the effective Hamiltonian, which is much smaller in terms of the dimension, because we only care about the small subspace. Then we work with this effective Hamiltonian and get the energy. Right? So this one is more helpful because in real case, we may care we may not only care about the energy, we also care some other properties. In that case, we can calculate some quantities directly from this small effective Hamiltonian instead of working with this kind of a large Hamiltonian. Okay, so I will write down the formula for the effective Hamiltonian and then to show you guys their equivalent. So the effective Hamiltonian is given by, so assuming the degenerate space, the energy, original energy is E naught plus PV P. So V is this V. And P is a projection operator. Basically project my state onto this subspace we care about. And so V is just the V here. And this R is known as resonance. It's defined like this. And this P is still the projection operator. Okay, so you may look, this looks like quite complicated, but you can write down term by term. E naught plus when n equal to 0, it's just PVP. When n equal to 1, it's just a PV E minus E naught inverse 1 minus PV and P. So this is to second order. To second order, we can replace this energy with E naught, right? So this is basically the formula we need up to second order perturbation. So if the first case, if the subspace we care about is one dimension, basically we care about one energy level. Let's say it's cat n, and the original energy is En. Then this effective Hamiltonian becomes just a number, right? Because it's just a one dimension, so it's a number. And this number is nothing but the energy we would get from the standard perturbation. To say that, let's say, okay, so and equal E naught plus P and PV Pn plus PV. This guy you can of course write in this form like this. And in this case, P, remember P is a projection operator, so it's N, right? project all the states onto the state we care about. E naught plus n right? So this P projection operator acting on this cat n trivially, right? Because it's like this. This guy is 1, so it's still cat n. However, for this guy, looks very complicated, but it's okay. It's not that. Okay. This is this. So here we insert identity. This. By the way, this 1 minus p, just like a project your state outside the space we care about, right? So this, by the way, this is a zeroth order. This is nothing but the first order perturbation. Now we want to say this guy is nothing but the second order perturbation. To see that is this p acting on n trivially. So it's like this. And so this guy project this n. So once your p 1 minus p acting on your n, it will get like this. Your n must be some other energy levels outside your subspace you care about. And this guy can be replaced. Sorry, this is with EM. Now you can say it's nothing but like this. So this is equivalent to our standard perturbation. You may think, okay, for one energy level, it's kind of we spend kind of work so hard and produce the same result is kind of useless. But this is powerful, especially for the degenerate case. So let's give you guys an example. Imagine I have a Hamiltonian, looks like this. Now I want to ask you to calculate the energy correction in the subspace. Like there's a degenerate subspace, right? To second order. Okay, so if you naively apply the formula you have, you will get the wrong result. This is actually one comprehensive exam. I just took it from previous exam. This because for the second order degenerate perturbation theory, we usually assume after the first order perturbation, the energy levels no longer degenerate. Then we apply the standard non-degenerate perturbation to the kind of a degenerate space to get the second order. But in this case, after the first order perturbation, the degenerate space is still degenerate. Then your standard formula breaks down. You cannot just apply it naively. Did you get what I'm saying? Okay. But this
From just
formula.
looking at the matrix, the fact that that the first order won't lift the perturbation.
Sorry.
Is there a way we could read off just looking at that matrix the fact that a first order?
Yeah, it's clear, right? It's clear. It's clear. Yeah.
Okay.
Yeah. 0. Yeah. So basically, the first order perturbation for the degenerate space is nothing but diagonalize this guy, right? Now it's already diagonalized and it's still degenerate, right? So in this case, if you naively apply the formula you have in the textbook, you would get a wrong result. That's the trick of this problem. That means you need to rederive a formula by yourself. But that's not fun. And you can derive it, like spend a long time, but actually this guy is still true. Yeah. So let me reproduce, let me derive the effective Hamiltonian for this degenerate subspace, meaning that it's a 2x2 matrix. So somehow, in this case, your Hilbert space is 3-dimension, but we only care about kind of a 2-dimension, right? Subspace of 2-dimension. So we can construct an effective Hamiltonian out of this 3-dimensional Hamiltonian and get some elements and then diagonalize this guy, we would get the correct result.
So just to make sure, that 3x3 like Hamiltonian is the full Hamiltonian, right?
Yeah, it's a full Hamiltonian. By the way, of course, there's an assumption is A, B is much smaller than the difference between the energy level. So we can treat the A and the B as perturbations.
So in degenerate is degenerate after the first order, even after.
Yeah. Usually like for the degenerate space, the degenerate space is no longer degenerate after the first perturbation, and then we apply the non-degenerate formula to that, and we get second order perturbation for the degenerate space, right? That's how we derive it in textbook.
So you're not gonna tell about like the 0th order degenerate while it splits after the first order.
Sorry, this is okay. So up to 0th order is E1, E2. Sorry, E1. 0th order looks like this, right?
Yeah.
And to second order, imagine if this is epsilon, this is another epsilon, then second order, to first order, the energy I guess would be E1 plus epsilon, E2 minus E1 minus epsilon. In this case, your subspace no longer degenerates, and then you can apply the standard formula you have.
But these are like solved by directly diagonalizing the full Hamiltonian instead of using the perturbation theorem.
No. I only I diagonalize this part. Okay, yeah. You're right. Of course, this is a 3x3 matrix. You can diagonalize this matrix directly without involving any perturbation theory. That's in that case you would get the exact energy, and you can compare your perturbation with your exact energy. That's actually the complete problem. First, you diagonalize this Hamiltonian with like directly without any perturbation, then you get the direct E1, E2, E3. It's the exact answer. Then now this is a part A. Part B asks you to do the kind of a perturbation. If you naively apply this kind of perturbation to the degenerate space, you would get a wrong result. What I mean by so when I say it's a wrong result, I mean if you do ternary expansion for your correct result, you won't get this perturbation, right? You would expect if you do the ternary expression for your exact result, like around some small parameters, like for example, a minus e1 minus e2, you should get some, you should get the results that you get from the perturbation, right?
Okay.
Okay, so anyway, so I will do one element for you guys. You can do the other elements by yourself, but okay, so for example, for the 1, 1 element, it's given by, so the first guy is E1, right? This guy is 0, right? This guy is more complicated, but it's 1 V E naught minus H naught minus P V 1, and this guy is equivalent to 1 V E naught minus H naught 1 minus P and 3 V1. And I can erase this 1 minus P. And this is 1. So it's nothing but E1 minus E2, E1 V3, 3 V1, which is E1 minus E2 A squared. So the first element of my effective Hamiltonian is given by E1 plus E1 minus E2 A squared. And eventually you would get a, I guess in this case it's a 1 plus B squared. You can do these elements by yourself. And this one is E1 minus E2 AB star E1 minus E2 A star B. And then if you diagonalize this guy, you would get the correct result, which is, I think it's one energy is E1, remains the same, and another energy is E1 plus A squared plus this. If I remember correctly, if you apply the second order perturbations formula for the degenerate space, like to this case, you would get lambda equal to E1 plus some E1 minus E2, some A squared, or lambda equal to some E1, some B squared, something like this. I didn't remember exactly, but something like this. It's different from this result. Yeah, let me know if you have any question. Yeah, I guess I'm pretty sure this will not be tested in your exam, but I think it's useful for you guys to
actually, Yaroslav talked about that in the lecture.
Yeah, this is how he derived the perturbation expansions, but he didn't make like a big deal about how this was more general.
I see. I see. Yeah, I mean this as this is already very mm, yeah, it looks very similar to what you have in the perturbation, like the expression, right? You can see there are some like a e minus h and yeah. Yeah. Yeah, I guess the time is up. So if you have no question, you're free to go.